Hello everyone. Today I will talk about the Fourier series expansion of a function fx. Joseph Fourier in 1822 proposed a trigonometric series while he was solving the questions related to the heat equations. After some initial investigation done by Euler, this series was known as the Fourier series expansion of the function fx. So I am starting with the definition. An infinite series or in infinite trigonometric series a0 upon 2 plus an cos nx plus bn sin nx is known as Fourier series expansion of fx. Fourier series of fx where our fx is periodic of length 2 pi defined in interval c, c plus 2 pi. So this infinite trigonometric series is known as the Fourier series expansion of fx, where fx is periodic of length 2 pi defined in the interval c, c plus 2 pi, and the coefficients a0, a and bn are known as Euler formulae, where my an equal to 1 upon 2 pi, say 1 upon pi from c plus 2 pi, then fx cos nx dx. Here my n is from 0, 1, 2 and so on. Now if we put n equal to 0, then this Euler coefficient, Euler formula a0 will be 1 by pi c to c plus 2 pi fx dx. That is the value of a0. Then your bn is equal to 1 upon pi integral c to c plus 2 pi fx sin nx dx. So these are known as the Euler formulae and can be calculated very easily. Please note that the trigonometric expansion a0 by 2 an cos nx plus bn sin nx, the Fourier series of fx converges to fx. Please note that if the Fourier series of fx converges to fx, only then that representation will be valid. Only then we will have a valid representation. So that means the Fourier series should converge to a function fx. Now what are the conditions behind the convergence? So for that we have a sufficient conditions of Dirichlet. So Dirichlet condition of convergence. Dirichlet condition of convergence. Dirichlet said that the trigonometric series of fx defined of fx with period 2 pi defined in interval c, c plus 2 pi can be expanded. The trigonometric series of fx with period 2 pi, which was defined in the interval c, c plus 2 pi, can be expanded in the trigonometric series a0 by 2 plus n equal to 1 to infinity an cos nx plus bn sin nx this trigonometric series can be expanded in this form only when your can be expanded in this form if where your a0, an and bn are constants, if the first condition that the function fx has to be periodic, as we can say that here we have assumed that it is periodic of period 2 pi. So fx has to be periodic and bounded in the interval c, c plus 2 pi. This is the first condition. Then in the second condition, fx has to be continuous, or you can say piecewise continuous. Fx has to be piecewise continuous with only finite number of discontinuities in interval c, c plus 2 pi. This is the second condition. Then the third condition, and which is the last condition, that fx should have at most finite number of maxima and minima. In the interval c, c plus 2 pi. If these three conditions holds, then only we see that fx have at most finite number of maxima and minima in this interval c, c plus 2 pi. If these three conditions holds, then we will say that this trigonometric series converges to fx. Only then we will say that it will converge to fx. So while we solve the questions, we will assume that these three conditions satisfied. So only when these three conditions are satisfied, we will try to solve the question. And now if this series converges to fx, then what is the value of this particular series at some point? So now suppose that this series converges to fx. Now let us compute the value of the function at some particular point. Please note down these formulae very carefully, because we will need these formulae during the questions. Now, if fx is continuous, then your value of the function, then the sum of trigonometric series, is f of alpha. That means the trigonometric series a0 by 2 plus summation n equal to 1 to infinity an cos nx plus bn sin nx will have this summation f of alpha at some alpha, where alpha will be the point of the interval. So if alpha is the point of this interval, then the sum of the trigonometric series will be f of alpha. Second, now suppose that alpha is a point of discontinuity. Now if alpha is an interior point of discontinuity in the interval c, c plus 2 pi, then suppose that if alpha is the interior point of discontinuity in this interval, then the value of the function alpha, now here our function is not continuous, our function is discontinuous. So if the alpha is a point of discontinuity, then the sum of the trigonometric series will be 1 by 2 the left hand limit at alpha plus the right hand limit at alpha. So the value of f of alpha will be the average of the left hand limit at alpha plus the right hand limit at alpha. So this is the case when the function is discontinuous at some interior point. Now third, if alpha is a point of discontinuity point of discontinuity at either x equal to c or x equal to c plus 2 pi. That means if alpha is a point of discontinuity at the end points, then our f of alpha will be the sum of the series will be the average of the right hand limit at c plus the left hand limit at c plus 2 minus pi. So the sum of the series will be the right hand limit at c and the left hand limit at c plus 2 pi. Okay. Now suppose that our c is 0. Let us write two different series for the interval 0 to 2 pi and from minus pi to pi. Note, if c equal to 0, then Fourier series in interval. Now if c is 0, then our interval was from c to c plus 2 pi. Now this will be from 0 to 2 pi, and our Fourier series will be a0 by 2 plus an cos nx plus bn sin nx. Now where our a0 will be 1 upon pi minus pi to pi fx dx, and an will be 1 upon pi 0 to 2 pi fx cos nx, and bn will be 1 upon pi 0 to 2 pi fx sin nx. So if the interval will be 0 to 2 pi and the function will be periodic of period 2 pi, then our Fourier series will be this one, where the Fourier coefficients are a0, an and bn given by these three Euler formulae. So this is the Fourier series for the interval 0, 2 pi. Now let us write the Fourier series for the interval from minus pi to pi. Now if c equal to minus pi, then our Fourier series will be, our interval will be c, c plus 2 pi. Now c is minus pi, so this will be a minus pi, plus pi. And then our Fourier coefficients will be this one. So if the interval is from minus pi to pi, then our Fourier series will be a0 by 2 summation an cos nx plus bn sin nx. Now please check your original series, which was your c to c plus 2 pi. Now if c is minus pi, then this will be a minus pi to pi fx dx. C to c plus 2 pi. Now as c is pi, so this c is minus pi, so this will be from minus pi to pi fx cos nx dx, and bn is this one. Now let us try to solve some questions related to these two intervals. First question, solve fx equal to x minus x square in the interval minus pi to pi, or in the interval minus pi to pi, and deduce this summation 1 upon 2n. So deduce this series 1 upon 1 square minus 1 upon 3 square, 1 upon 2 square plus 1 upon 3 square minus 1 upon 5 square, and so on. Deduce this series. Solution: fx equal to x minus x square. So our Fourier series is fx equal to a0 upon 2 plus n equal to 1 to infinity an cos nx plus n equal to 1 to infinity bn sin nx. This is our Fourier series. Okay, where my a0 will be 1 upon pi minus pi to pi fx dx. So this will be 1 upon pi minus pi to pi fx means x minus x squared dx. Here you can see that x dx is the odd function. So x dx is the odd function, so the integral minus pi to pi x dx will be 0. using the property of the definite integral. And x square dx is the even function, so integral minus pi to pi x square dx will be 2 times 0 to pi x square dx. So this is equal to 1 upon pi. The first integral will be 0, and for the second integral we will have minus pi to pi x square dx. So this will be your 1 upon pi. Now this will be your 2 times 0 to pi x square dx. Now the integration of x square is x cube upon 3. So this will be your x cube upon 3. So putting the upper limit we will get minus 2 pi square upon 3. So this is your a naught. Now an will be 1 upon pi minus pi to pi fx cos nx dx. So this is equal to 1 upon pi minus pi to pi fx was x minus x square cos nx dx. Now here you can see that x is odd function, cos nx is even. So their product will be odd function. So integral minus pi to pi x cos nx will be 0. X square is even, cos nx is even. So integral minus pi to pi x square cos nx will be 2 times. So the first integral is 0 because the function is odd, and for the second term this will be your 2 upon pi, this will be your 2 times integral 0 to pi x square cos nx dx. So this is equal to minus 2 upon pi integral 0 to pi x square cos nx dx. This will be minus 2 upon pi 0 to pi x square cos nx dx. Now we will use the Bernoulli rule of integration. The Bernoulli rule of integration is uv is equal to u, then the integration of b, that is your b1, then u dash, the integration of b1, say that is your b2, plus u double dash, integration of b2, and so on. Now here we will use the Bernoulli rule of integration. We will assume u as x square. So an will be minus 2 upon pi. So the x square into integration of cos nx. Integration of cos nx means minus sin nx upon n. Then we will use minus sign, then the derivative of x square, that is your 2x, then the integration of this bracket, which is your minus cos nx upon n. Then we will have plus sign, then the differentiation of 2x will be 2, and then integration of this bracket will be sin nx upon n. Here we will have n square, and here we will have n cube, because the integration of sin nx upon n will be, integration of sin nx will be minus cos nx, and we will have one n in the denominator. So this will be your minus minus plus, because the integration of sin nx will be minus, so minus minus plus, and one n will come in the denominator, so this will be your n square, and the integration of cos nx is sin nx upon n cube, and the limits from 0. I think there is some mistake, because the integration of cos is plus sine, and the integration of sine is minus cos, and there will be minus sine. So now it is correct. So this is equal to minus 2 upon pi. You can see that here sin pi will be 0, sin 0 is 0, sin n pi is again 0, and sin 0 is 0. So the upper and lower limit of this term and this term will be 0. Now the upper limit of this term will exist, and the lower limit will be 0. So this is your minus minus plus 2 times x means 2 times pi, and then minus minus is plus, and then cos n pi, which is your minus 1 to the power n, because cos n pi is minus 1 to the power n. So this is equal to minus 4 minus 1 to the power n upon n square. So this is the value of an. Now let us compute bn. Bn equal to 1 upon pi minus pi to pi fx sin nx dx. So this will be your 1 upon pi minus pi to pi fx was your x minus x square sin nx. Here you can see that our x square is even, sin nx is odd, so their product will be odd, and x into sin nx is even function because x is odd function, sin nx is odd function, so their product will be even function. So this will be your 1 upon pi minus pi to pi x sin nx. Now this is your odd, that is your odd, so product is even, and here is the even and it is odd, so their product will be 0 because product is odd function. So this will be your 2 upon pi 0 to pi x sin nx dx. Now use the Bernoulli expansion of integration, then it will be your x, integration of cos and sin nx will be cos nx upon n, then we will have minus sin, and then differentiation of x is 1, and integration of this cos will be your sin nx upon n, so this will be your n square, and the limits from 0 to pi. Here you can see that our upper limit and lower limit both are 0, and the lower limit of this will be 0 and the upper limit will be 2 upon pi. At x equal to pi, this will be a pi minus cos n pi, this will be a minus 1 for n divided by n. So you can see that our bn is equal to this term. So this is your bn. Hence the Fourier series expansion is, therefore the Fourier series is a0 upon 2 plus n equal to 1 to infinity an cos nx plus bn sin nx. Now therefore our fx was x minus x square. Now a0 was minus 2 pi square upon 3, so this will be a minus pi square upon 3. Now n equal to 1 to infinity an. Our an was minus 4 into minus 1 to power n upon n square, and our bn is minus 2 minus 1 to power n upon n sin nx. As we need the sum of a particular series, which was your 1 upon 1 square minus 1 upon 3 square and so on, 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square and so on. So as square term is there, so we will try to banish this term. To remove this term in the expansion, let us put x equal to 0. So if x equal to 0, then your left hand side will be 0, and at the right hand side we will have minus pi square upon 3. Now as cos 0 is 1, so this will be your n equal to 1 to infinity. This minus and minus will be minus 1 to power n plus 1 divided by n square. So thus pi square upon 3 is equal to 4 times n equal to 1 to infinity minus 1 to power n plus 1 upon n square. Thus you can say that now if n is 1, then this will be your 1 upon 1 square. If n is 2, then this will be your negative. Then we will have plus sign and so on. This will be equal to pi square upon 12. So this is your answer. Let us solve one other question, which is your find Fourier series of fx equal to, let us find out the Fourier series of this fx, where my fx is equal to minus pi when your x is between minus pi to 0, and it is x when your x is between 0 to pi. Let us find out its Fourier series. Solution. Fourier series is a0 by 2 plus n equal to 1 to infinity an cos nx plus n equal to 1 to infinity bn sin nx, where my a0 will be 1 upon pi minus pi to pi. Here you consider the function is periodic with the period, means the length of the interval, which is your 2 pi. So the value of the a0 will be 1 upon pi minus pi to pi fx dx. Now let us break this interval in two parts, that is from minus pi to 0 and then from 0 to pi. Now you can see that from minus pi to 0, the value of the function was minus pi. So this will be your integral minus pi to 0 minus pi dx, and for the second part we will have x dx. So this is equal to minus pi, then the integration of dx will be x. So the limits will be, the upper limit is 0 and the lower limit is minus pi, so this will be your pi. And here the integration of x will be your pi square by 2. So this is your minus pi square minus 2 pi square plus pi square, that means minus pi square by 2. So this is your minus pi by 2. So your a naught is minus pi by 2. Now an is equal to minus 1 to pi. An is equal to 1 upon pi minus pi to pi fx cos nx. So this is equal to 1 upon pi, then integral from minus pi to 0, and this integral, our value of the function was minus pi. Then integral 0 to pi, and for this part our value of the function was pi. For this part the value of the function was x. So this is equal to 1 upon pi. Now the integration of cos nx will be sin nx upon n. Now you can see that the upper limit and lower limit both will be 0, because sin 0 is 0 and sin n pi is 0. So this term will be 0, and for this part x, let us integrate this one by the Bernoulli rule. So x into the integration of cos nx means sin nx upon n, then minus sin differentiation of x, and then the integration of sin nx, which is your cos nx upon n. So the limits from 0 to pi. So you can see that our an is equal to, now the first term is 0. Here you can say that upper limit and lower limit both are 0. So here the upper and both upper and lower limit will exist, and this will be 1 upon n square, and the upper limit will be your cos n pi, so that is your minus 1 upon n, and the lower limit is cos 0, that is your 1. So your n will be this one, 1 upon n square pi. Your n will be 1 upon n square pi minus 1 upon n minus 1. And you can see that if n is odd, then this is your minus 1 and it is minus 1, so this will be minus 2 times. If n is even, then this will be your plus 1 and that is your minus 1, so this will be your 0. Now Bn, so this is equal to 1 upon pi minus pi to 0. Fx was your minus pi sin nx, then we will have 0 to pi, and for this part fx was x. So now let us integrate this term. This will be a minus pi. Integration of sin will be minus cos nx upon n. The limits from minus pi to 0. Now here we can use the Bernoulli rule. This will be your x into the integration of sin nx. Then we will have minus sin. Then we will have minus sin, and again this will be your minus sin nx upon n square. And then the limits from 0 to pi. Okay. Now we can see that its upper and lower limit will be 0. So this term will be 0. Here the upper limit will exist, and for this both upper and lower limit will exist. So this is your minus minus plus pi. So this is your pi. In the bracket we will have cos 0, that is 1. And for the lower limit we will have minus 1 power n. And in the denominator we have n. For this will be your minus pi upon n. Now the upper limit will be cos n pi. This is your minus 1 power n. Now we can combine these two terms, and therefore our answer will be, this is your 1, and this term can be combined, so this will be your, this one. So the Fourier series is thus fx equal to a0 upon 2, n equal to 1 to infinity a n cos nx plus dn sin nx. So please remember that in this case function is discontinuous, so we cannot write fx as a particular value. Now a0 was minus pi by 2, so this will be your minus pi. Now an is 1 upon n square pi, minus 1 upon n minus 1. This was my an. This was my an, yes. And our bn is 1 upon n, 1 minus 2 minus 1 power n sin nx. So this will be your Fourier series expansion of the function fx. Now as we have to get the particular series, so let us put equal to 0, then now as x equal to 0 is a interior point of this interval, and we can see that the function is discontinuous at x equal to 0. So our f0 will be the average of the right hand limit at 0 and the left hand limit at x equal to 0. Please note that our fx was this one, minus pi, when your x is between minus pi to 0, and this was your plus x when your x was from 0 to pi. Now you can see that if x is greater than 0, then your f0 will be 0, because fx is x, so as x equal to 0, so this f0 plus will be 0. So the first term is 0. Now if x is less than 0, then your f0 is minus pi, so this is your minus pi, and we will have minus pi upon 2. I think here is a mistake, as our a0 was minus pi by 2, so this will be a minus pi by 4. a0 was minus pi by 2. So now put x equal to 0 in this series. So if x equal to 0, then our left hand side was minus pi by 2. Now in the right hand side we will have minus pi by 4 plus summation 1 upon n square pi minus 1 to power n minus 1. Now cos 0 is 1 and sin 0 is 0. So this term will be 0. So this is equal to pi by 4 minus pi by 2 is equal to 1 upon pi. Now if n is 1, then this will be your minus 1, and that is your minus 1. So this will be minus 2 upon 1 square. If n is 2, then this will be your plus 1, and that is your minus 1. So this is 0. Again, if n is 3, we will have minus 2. So minus 2 upon 3 square, then minus 2 upon 5 square, and so on. Now here, this will be your 2 pi minus 4 pi divided by 8. Or you can say that our LCM is 4, so this is your pi minus 2 pi. So equal to minus 2 upon pi, and in the bracket we will have 1 upon 1 square, 1 upon 3 square, 1 upon 5 square, and so on. So this is equal to, now this will be a minus pi by 4, so this will be a pi square by 8. So the sum of this series is equal to pi square upon 8. So thank you for being with me in this lecture. In the next lecture I will try to solve some other questions related to the Fourier series expansion of the function fx.